Hello there and welcome back to this course summary of electrical circuits and networks. And in this video, we are going to discuss some circuit theorems that will help us analyze circuits. So in the previous video, we have discussed the superposition theorem. And moving on from that, we have here Thevenin theorem, Norton theorem, maximum power theorem, and before that, substitution theorem. So let's start. So before going into Thevenin theorem, I'll just like to speak about the substitution theorem, where basically there is a network of resistors, the network of components, and a, a particular component, a resistor, has been separated for observation, and it is seen that current IR flows through it, and it sees a potential drop of VR. Rest of the network is along with it. So basically, the substitution theorem says that this particular resistor, the current through which is IR, can be replaced by a constant current source of IR current or a constant voltage source of potential difference VR. And why is it so? The proof is quite simple. We can just have equal and opposite currents IR connected in parallel to the resistor, which will make no difference because the current will be confined to the loop of the sources. And then we can, since they are in parallel, we can just rearrange them such that the resistor comes to the rightmost part of this diagram. And since the resistor and source on the right part of this diagram form their own loop as they did before, we can just separate out this loop and you can see that IR is left alone with the network. Same goes for voltages. We can have two equal and opposite voltages connected in series such that they make no difference to the uh, current or voltage in the network. And again, we can see that from let's say coming out from the terminal of the network, we have a potential drop of VR, again a potential gain of VR, and again a potential drop of VR through the resistor. So equivalently, the voltage source and the resistor make no difference, make no potential difference. So we can just remove those parts by and connect the rest of the circuit with a wire being short circuited, and that's how we can replace it with a potential constant voltage source of VR with a potential difference VR. So this can help us replace a resistor in any network with a voltage source or a current source such that it makes no difference to how the circuit has been arranged. Okay, now having understood this, let's move on to the Thevenin theorem. What Thevenin theorem has got to say? Okay, coming on to this page. So basically, any network of linear elements will be comprising of resistors, as of now, then current sources and independent sources. Let's say this network, we take two terminals at two nodes of this network. As you can see in the first diagram here, that and those two terminals have been connected with a, let's say we put a resistor across those two terminals and we found that current Ix was flowing through the resistor, and by substitution theorem we put a constant volt current source Ix over there. So basically we want to reduce the entire network to uh, something very short and uh, easy to understand the entire circuit, entire network, however large it may be. So this is an attempt to do so. Well, by superposition theorem, we'll apply superposition theorem to reduce the circuit. Let's see how it can be done. So basically, the output of the network at this terminal will be the superposition of the network with uh, independent sources plus the output without independent sources. So let's do the two steps. Step number one, we have the linear network and we have the independent sources, and what we do is we just short circuit sorry I mean we open circuit the terminal such that no current will flow through it and measure the potential difference across the terminal. We note this and call it VTH. Now in step 2 we will just null all the independent sources, that is voltage sources will be short circuited and current sources will be open circuited in the network, and now we will put a, let's say a constant voltage source outside to connected to the terminal, let's say Ix, and there will be a potential difference as well. So we measure the potential difference and the current flowing through this terminal, measuring the potential difference across the ends and the current Ix flowing through it. And since the components are linear, we are bound to get a relation, something like Vx is R dash times Ix, where R dash will be having dimensions of a resistor, and we call R dash RTH. Now, combining these two, we can see that the output of the terminal, the output voltage, let's say, output voltage Vx can be written as VTH, which we found in the first case, minus Ix times RTH. This is because in the second case, if we since we don't have independent sources, it can be the entire network can be considered as one resistor. We will have a potential drop across it. So while going through the loop, it can be understood that the VTH will be decreased by Ix times RTH amount when we superimpose it. And after that, once we have the output voltage equation, that is VTH minus Ix times RTH, this can be understood with a circuit which is given below, that is a potential source VTH, a resistance RTH, and a current source Ix attached to the terminals. This is true for any Ix, and VTH and RTH are what we call Thevenin parameters, Thevenin voltage and Thevenin resistance. So this was how the theorem came up. But in short, what we need for problem solving is just VTH and RTH. Once that we know what the theorem is, so how to do that? Basically, for VTH, just open circuit uh, the terminal, just measure the potential difference across it, call it VTH, then null all the independent sources, and measure the resistance across the resistance across the terminals, call it RTH, and you're ready to go. That is all Thevenin theorem has got to say. That is, once you have VTH and RTH, you have the equivalent of the system, and you can connect it to the other network or other current sources, resistor or whatever. And thus we have simplified to a great extent a big network to just a voltage source and a resistance. In the next video, we'll try to understand a dual of this theorem, that is the Norton theorem, and another circuit theorem, uh, that is the maximum power theorem. Thanks for watching and see you there.